Hello dear students, welcome back to the discussion NCERT line by line questions. Now we discuss the chapter wave optics. Okay, moving to the questions. First one, the phenomenon of diffraction takes place for sound waves only. Okay, sound waves experience diffraction. Okay, what is diffraction? Is the bending of the light around the corners of the obstacles. Sound waves diffract very well. Light waves only. Light waves also diffract. Matter waves, for example, the wave pattern due to the motion of electrons. Okay, electrons are having diffraction. Clear? That's proved by Davison and Germer experiment. Okay, the wave nature of electron. So the diffraction phenomenon is there for all these three types of waves. So answer is option D, or fourth one. Okay, the next one. If Young's double slit experiment uses a monochromatic light, the shape of fringes formed on the screen is actually the fringes in this way. Okay, the shape of fringes formed on the screen is hyperbolic in nature. Okay, yes. The next one. A diffraction pattern is obtained by using a beam of red light. What will happen if red light is replaced by blue light? Okay, what's happening? Red is replaced by blue, which means the wavelength is decreased. That is, lambda is decreased. Wavelength of the wave is decreased. Wavelength of the wave is decreased. Okay. Then what happens to the bands? We have the bandwidth. Actually, this is of diffraction pattern. Even though we can define the bandwidth as we define in the case of Young's double slit experiment, the bandwidth is lambda d by d. Okay. Here, d is the width of the slit. We can use so width of the slit, and d is the screen distance from the slit. Clear? This is the slit, you know, this one, this is D, and here is the screen. The screen distance is capital D. Clear? Then this bandwidth, the size of the band is directly proportional to lambda. Yes. Here red is replaced by blue means lambda is decreasing, means bandwidth is decreasing. The bands are reduced. The bands are becoming narrow. Okay, diffraction bands becomes narrow and crowded. Answer is option C. Okay, next one. Which of the following is correct for light diverging from a point source? From a point source, light is diverging. Okay, the intensity changes in proportion to the distance squared. Intensity directly proportional to the square of the distance is incorrect. Clear? The wavefront parabolic is incorrect. Wavefront are spherical. Okay. The intensity changes inversely proportional to distance squared. That is true. Intensity proportional to 1 by r square. That is true. The intensity changes inversely proportional to distance is incorrect. Our answer is the third one. Okay. Yeah. Next. In Young's double slit experiment, the slits are separated by 0.28 millimeter in YDSC. Young's double slit experiment, the separation of the slits symbolized by D, 0.28 millimeter, 10 power minus 3 meter. Okay. Screen is placed 1.4 meter away. Screen distance is 1.4 meter away. Okay. The width of the bright fringe is measured to be 1.2 centimeter. Beta fringe width 1.2 centimeter. The wavelength of the light used in this experiment, very direct, we have fringe width beta is lambda d by d. Okay, then we have lambda is equal to beta into d divided by d. Direct. 1.2 into 10 power minus 2 into 0.28 into 10 power minus 3 divided by 1.4. Okay? Yes. This one we can write 2.8 into 10 power minus 4. Then 2.8 and 1.4 cancelled. We get 2 into 10 power minus 4. 2 into 1.2 is 2.4. 2.4 into 10 raised minus 4, then 10 power minus 2 is 10 power minus 6. 2.4 into 10 power minus 6, option A. Yes. The next. The angle between the axes of two Polaroids is 30 degree. Consider two Polaroids symbolically represented like this. Okay. Okay. Their pass axes are at an angle of 30 degree. Okay. Yeah. The ratio of intensities of the emergent and unpolarized incident light will be. Consider an unpolarized. This is the unpolarized wave. Suppose. Let its intensity be I naught. Okay. After coming out of the first Polaroid, it becomes polarized and its intensity is reduced to half. I naught by 2. Okay. And this polarized is entering into this another Polaroid. Okay. And this is again polarized and its intensity I is equal to the intensity entering into, that is I naught by 2, the intensity entering into cos square theta times. Cos square theta times. What is theta? Is the angle between the pass axes. That is 30 degree. Understood? Okay. This is called Malus law. Okay. The intensity of emergent polarized is equal to the intensity of incidenting polarized into cos square theta. This is I naught by 2 into cos 30 is root 3 by 2. Its square is 3 by 4. Clear? Yes. Then, how much times of the unpolarized intensity? Unpolarized intensity into 3 by 8. 3 by 8 times 3 by 8. Okay. The ratio of intensity of the emergent. The ratio of intensity of the emergent divided by unpolarized intensity is equal to 3 by 8. 3 by 8 is the answer. Okay. Good. Yeah. The next one. In Young's double slit experiment, the phase difference between two waves reaching at a point is pi by 3. YDSE. What is that? Young's double slit experiment. The phase difference of two waves hitting at a point in the screen is given pi by 3. Okay. Yes. The intensity of this point expressed as a fraction of maximum intensity I naught is. Maximum intensity in the screen. We have the intensity of the light at a point in YDSE is equal to maximum intensity I max into cos square of 5 by 2. This relation we studied. It's very clear. I max into cos square of, what is 5 here? Pi by 3. By 2, pi by 6. Pi by 6 is 30 degree. Cos square of 30. Cos 30 is root 3 by 2. Square is 3 by 4. I max into 3 by 4. That is the intensity at that point. Okay. 3 by 4 of the maximum intensity. Here in the question, maximum intensity noted as I naught. 3 by 4 of I naught. Option 4. Good? Yes. The next one. When a low-flying aircraft passes overhead, we sometimes notice a slight shaking of the picture in our TV screen. This because of dash between the direct signal and reflected signal interference. direct signal and the reflected signal are interfering. That's why. Okay, moving to the next one. The idea of secondary wavelets for the propagation of light wave was first given by Christian Huygens. Okay, wave theory introduced by Christian Huygens. Okay. The ratio of the amplitude of the two sources producing interference is 3:5. Two sources, S1, S2. Okay. The waves coming from these two sources are having amplitude ratio A1 by A2 is equal to 3/5. Okay. The ratio of intensities at maxima and minima. Okay. What is the ratio of I max to I minimum in the interference pattern? We have to study the formula. I max divided by I minimum is A1 plus A2 whole square divided by A1 minus A2 whole square. Okay. I max is proportional to A1 plus A2 whole square. I minimum is proportional to A1 minus A2 whole square. Yes. Clear? Yeah. See, A1 is equal to 3/5 of A2. Otherwise, we can place A1 as 3, then A2 as 5. 3 and 5. Actually, A1 is not 3 and A2 is not 5. If we put A1 as 3, then we can assume A2 as 5. Otherwise, we can place instead of A1 here 3/5 of A2. 3/5 of A2, then plus A2. 3/5 of A2 minus A2. A2 cancel. Okay. That is the exact method. 3/5 of A2 plus A2 divided by 3/5 of A2 minus A2 the whole square. This is the actual apt way. A2 cancelled. Understood. 3/5 plus 1. That is 3 plus 5 divided by 5. All divided by 3/5 minus 1. That is 3 minus 5 all divided by 5. All square. 1/5 cancel. 3 plus 5 is 8. 3 minus 5 is minus 2. It's square. 8 square is 64 divided by minus 2 square is 4. 64 by 4 is 16 is the answer. 16:1 is the answer. Okay. The simplest way is put here 3, here 5. Then what it is? 8. Here 3, here 5. Minus 2. Square it. We get the answer 16. Understood? Clear? Next. Colors of the soap bubble is due to interference of the waves coming from different layers. That's why. The next one. Intensity of a bright fringe in a single slit diffraction pattern on a screen is same for all bright fringes. No. That is a case of which one? Interference pattern. Okay. This is the case of diffraction pattern. The intensity is not same for all bright fringes. Intensity not same. Wrong. Increases and decreases alternatively. It is wrong. What's happening to the intensity as we move from the central bright fringe? The intensity goes on decreasing. And finally, the intensity reduces to 0. Yes. Decreases as we move away from the central bright fringe is the answer option C. This is incorrect. So answer is option C. 13th. Wavefronts associated with the point sources of wave is spherical. Point source spherical, linear source cylindrical. And the source at a far distance away. Wavefront will be plane wavefront. If the source is at a very large distance away. Okay. Point source spherical, linear source cylindrical. Okay. 14th. Light of wavelength 600 nm. Light of wavelength 600 nanometer. Incident on an aperture of size 2 millimeter. An aperture of size 2 millimeter. This wavelength is incident. The distance up to which light can travel such that its spread is less than the size of aperture is. Consider an aperture whose size is 2 millimeter and the waves are hitting. The waves are hitting and these waves are spreading. After passing through the aperture, the waves are spreading and that spread is called a diffraction. Okay. And the spreading effect is not significant for a particular distance. The spreading effect increases as we move away from the aperture. Spreading effect is increasing as we move away from the aperture. And the spreading effect is not significant up to a particular distance is called Fresnel distance. Okay? Up to the Fresnel distance, we can take this as rays or ray optics is valid. Ray optics is valid up to what distance? Fresnel distance from the aperture, and the Fresnel distance Z is equal to A square by lambda. Studied it. A square by lambda Fresnel distance. Okay. We have A is 2 millimeter, 2 into 10 power minus 3 square it. Lambda is 600 nm, 600 into 10 power minus 9. Okay. This is 4 into 10 power minus 6. This is 6 into 10 power minus 8 or 7. 10 power minus 7. Okay. 10 power minus 7. Clear? Yes. Then 10 power minus 6 divided by 10 power minus 7 cancelled. 10 remains here. Minus 1. 10 power minus 1 remains to the numerator. It is 10. 40 by 6. 20 by 3. 20 by 3 is 6.67 meter. See. From this 2 millimeter sized aperture up to 6.67 meter distance away, the rays are approximately in straight line and the ray optics is valid. Even from this small aperture of 2 mm size up to 7 meter range, the ray is straight. And the spreading is significant only after this 7 meter. This is why in day-to-day life, ray optics predominates. I think you understood. And this is the significance of Fresnel distance. Moving to the next one, 15th. The slits in YDSE are illuminated by light of wavelength 6000 angstrom. 6000 angstrom means 600 nm. Good. If the path difference at the central bright fringe is 0, path difference, then the path difference at the fourth bright fringe is path difference. See, path difference, we have the formula, path difference to get bright fringe is L lambda. That is very direct question. The path difference to get bright fringe is N lambda. And to get dark fringe is N plus half lambda. Studied the condition. Okay. Here the fourth. Clear? Okay. If N is equal to 0, it is the central bright fringe. Central. If N is equal to 1, it is the first bright fringe. After the central, there will be a minimum, then the first bright fringe. Then N is equal to 2. After the second darkness, there is the second bright fringe. If N is equal to 4, there is the fourth bright fringe. And lambda is 6000 angstrom. 10 power minus 10 is the angstrom, you know. Yes. Clear. Then this is 4 into 6, 24. 1, 2, 3. Then remaining is here 10 power minus 7. Then this is 2.4 into 10 power minus 6 meter in SI unit. 2.4 into 10 power minus 6 is the option A. Very direct. The next, the refractive index of a medium is root 3 n refractive index of a medium. If the unpolarized light is incidenting on it from air at the polarizing angle. Okay. The unpolarized light incidenting on a medium at polarizing angle. Polarizing angle is also known as Brewster's angle. Studied it, you know. Polarizing angle. Polarizing angle is the Brewster's angle. And here is a Brewster's law, you studied it. Brewster's angle IB. Brewster's angle IB. Clear? Yes. What is the situation is? Suppose there is a boundary connecting or separating two media. Okay. Unpolarized wave hitting. At what angle? At polarizing angle. What is polarizing angle? Otherwise called Brewster's angle IB. Okay. Some part of this is refracted and some other part is reflected. Okay. And if this angle of incidence is at Brewster's angle, then this reflected will be polarized. That is the condition we studied. Polarized. This is unpolarized. This is also unpolarized. Okay. The reflected will be polarized if and only if the angle of incidence is a particular angle named Brewster's angle. That's very clear. Okay. In this condition, what will be the angle between polarized and this one, or reflected and refracted, will be 90 degrees. Very important condition. When the reflected and refracted are perpendicular to each other, then the reflected will be polarized. Okay. Yeah. This one angle of incidence and this one angle of reflection, both are same. Both are same. Okay. That is the law of reflection. Okay. And this is IB. Then what about this remaining is 90 minus IB. 90 minus IB. Okay. And this is 90 minus IB. Then what about this one? This is totally 90, you know. Totally 90. Then this will be IB. And here it is IB means what will be this angle? This angle. This is totally 90, you know. Totally 90. Out of this IB means what about this one is 90 minus IB. Okay. And this 90 minus IB is the angle of refraction. Angle between the normal and refracted ray. That's the angle of refraction. Angle of refraction is 90 minus IB. When the ray hits at IB, polarizing angle, Brewster's angle, then the angle of refraction is 90 minus IB. And now when we apply the Snell's law here, we get Brewster's law. Sin IB divided by sin of 90 minus IB is equal to refractive index. Sin IB by cos IB is equal to refractive index. That is tan IB is the refractive index. That is Brewster's law. Okay. What's the question? The angle of refraction is 90 minus IB. Okay. And we should get what is IB? IB. What that is the Brewster's law. What is the Brewster's law? Tan IB is equal to refractive index. Tan of IB is equal to refractive index of second divided by first. Refractive index of second means that is n2 by n1 I can write. Here n2 is root 3, n1 is 1. From area to root 3. From area to this medium. From 1 to root 3. Okay. Then what about IB is equal to tan inverse of root 3 is 60 degree. 60 degree. Tan inverse of root 3 is 60 degree. The 90 minus 60 is 30 degrees the angle of refraction. 30 degree is the angle of refraction. Good. Next. When interference of light waves takes place. Interference takes place. Interference. Energy is created in the region of maximum intensity. Energy cannot be created nor destroyed. That is the basic principle. Okay, applicable in the universe, any part. The conservation of energy. Energy is destroyed, incorrect. Conservation of energy hold good and energy is redistributed is the correct answer. Okay, next. Two points separated by a distance of 0.1 millimeter can just be inspected in a microscope. Okay. 2 points separated by a distance of 0.1 can just be inspected, that is the limit of resolution 0.1 millimeter, that is we can write D minimum in the case of microscope. D minimum, that is the limit of resolution, the minimum distance between 2 points below which the microscope cannot resolve them. That is a point. Okay, here is a point, here is another point, we can easily resolve. When the points are get closer, and after a particular distance we feel them as a single one. Okay, that's the problem. We cannot observe the microorganisms or microbials here because our eye has a limit of resolution. While we use this type of instruments, microscope, limit of resolution is reduced. Okay. Here in this question, the limit of resolution given in the first case is 0.1 millimeter. When light of wavelength 6000 angstrom is used. When light of wavelength 6000 angstrom is used, the limit of resolution is 0.1 millimeter. Good. If the light of wavelength 8000 angstrom is used, then the limit of resolution will be, if lambda 2 is equal to 8000 angstrom, what will be the limit of resolution in that case? Okay. In the case of a microscope, we have the limit of resolution formula is 1.22 lambda divided by 2n sine beta. N is the refractive index of the medium between the object and the lens. Beta is the angle. Which angle? I think you remember that formula, you know. See, we have the figure. See, we have the figure here. This is the lens. In front of the object is the object. Okay. Principal axis. Okay. See, this ray. Here is an angle created, that is beta. And this medium has a refractive index, that is n. Okay, that's the formula. Clear? Yes. D minimum. So we understand this D minimum is directly proportional to lambda. Isn't it? This D, the distance between 2 points. The distance between 2 points directly proportional to lambda. Okay. Then what about D2 by D1 is equal to lambda 2 by lambda 1. D2 is equal to lambda 2 by lambda 1 into D1. Okay. Lambda 2 is 8000 angstrom. Lambda 1 is 6000 angstrom. D1 is 0.1 mm. That's our problem. Zeros are cut. 8 by 6 is 4 by 3. 4 by 3 is 1.33. Into 0.1 is 0.133 nm. 0.133 nm. As lambda increases, resolving power or limit of resolution is further decreased. Limit of resolution is increased. Limit of resolution increased means resolving power is decreased. Okay. In the first case, the microscope can resolve 2 points which are separated 0.1 millimeter away. In the second case, the microscope can only resolve 2 points which are separated 1.33 nm away. So as lambda increases, limit of resolution also increased, means the power of resolution is decreased. That's the point. I think you understood it. 0.13 nm is the answer. Okay? Yeah. Moving to the question number 19th. Transverse nature of light was confirmed by the phenomenon of polarization of light. Polarization. The light has transverse effect is proved by the phenomenon of polarization. The final question. A light of wavelength 550 nanometer. A light of wavelength 550 nanometer. Okay. Coming from a distant star. The limit of resolution of a telescope whose objective has a diameter of 2 meters is. The limit of resolution in the case of telescope is mentioned as angle. Okay. And the limit of resolution delta theta minimum, the minimum angle between two stars subtending at our eye or at the lens, objective lens. Okay, here is a star, and these are subtending an angle here, delta theta. Okay, this should be a minimum value. Okay, below which the two stars are appeared as a single one. That's the limit of resolution. Okay, and here is the formula 1.22 lambda divided by d. Direct, lambda is 550, d is 2. Okay, 1.22 into what is lambda is 550 into 10 power minus 9 divided by d is 2. Okay, solve it, we get 3.35 actually. Into 10 power minus 7, we get it. 3.35 into 10 power minus 7. Okay, here 3.35 but 10 power minus 6, 3.35 10 power minus 5, 3.38 10 power minus 7. So this is the approximate result. 3.35 into 10 raised to minus 7 is the answer of this question. Hope you understood all the questions clearly. All of them were very direct questions from which we get the idea or the concepts, basic concepts from the chapter. Okay. See you with the next NCERT line by line questions. Okay. Till then, study well. Thank you.